Here is the sixth structural design pattern. This one is called Flyweight Pattern, and it's a pattern you use when you want to share object instances across a very large data structure. I'll start with a quick summary of what we are trying to accomplish with this pattern. The flyweight pattern is a good choice when you are trying to accomplish the following. You want to support a very large number of fine-grained objects efficiently. The state information of each object can be retrieved on demand. Okay, let's elaborate on that. So, let's say I have an application where I use the composite design pattern to organize my data in a tree structure. The composite pattern organizes components into leaf objects, which cannot have children, and composite objects, which do have children. The leaves are at the edge of the tree structure, and the composites make up the intermediate levels. I have a super fast Redis database which contains millions of strings, and my goal is to build the composite tree structure by reading the database and copying each string into a unique leaf instance in the tree. Now here's the problem. If I create one unique object instance for each name, then I will end up with millions of leaf object instances in memory. And this is redundant because the names are already available in the Redis database. The flyweight pattern is the solution to this problem. The pattern performs a remarkable trick. It creates one single leaf instance and shares it millions of times in the tree. Every composite in the tree ends up referencing the same leaf object. Here's how it works. The first thing you have to do is examine the internal state of the leaf object and split it into an intrinsic state, which can be shared with others, and an extrinsic state, which cannot be shared. In my tree example, each leaf has a unique name, so I only have extrinsic state, which cannot be shared. The next step is to re-engineer the client code to always supply the extrinsic state. So every time my code accesses a leaf object, it must first look up the name in the database, and then provide this name to any method call in the leaf object. And the last step is to introduce a leaf object factory. The client code calls this factory every time it needs to create a new leaf instance, but the factory always returns the same leaf instance for each unique intrinsic state. Since my example has no intrinsic state, my factory will always return the same leaf instance. So you end up with a tree where every leaf node is the same object instance. And this works perfectly, because the client will always supply the name of the leaf for each operation. The flyweight pattern offers a number of benefits. First of all, the pattern allows you to create a huge number of virtual objects without having to explicitly instantiate every single one of them. This lets you build a detailed data structure like a tree or a graph, without having to instantiate each node. This will save a lot of memory if your data structure is very large. The pattern can help you not only reduce the memory footprint, but also speed up your code. If instantiating objects is an expensive operation, then the flyweight pattern will help you by recycling the same instance for each unique intrinsic state. This will reduce the number of times that the object constructor needs to be called. And finally, the pattern simplifies your code. Traversing a data structure where some nodes are instantiated and others are not is a complex operation. But the flyweight pattern hides this fact from the client. So the client code can enumerate a large data structure of virtual objects without having to worry which ones are instantiated and which ones are not. You can create very elegant code by combining the flyweight pattern with the enumerator or visitor pattern. This lets you efficiently enumerate a very large data structure. Okay, here is the UML diagram of the flyweight pattern. The pattern uses an abstract base class called Flyweight. This class has a single method called operation, and you can see that it expects the extrinsic state as an argument. The client always has to provide the extrinsic state for each flyweight object. There are two concrete subclasses of the flyweight base class. The first one, on the right, is called concrete flyweight, and this is the actual flyweight object. You can see in the diagram that it implements the operation, and that it also has a field called intrinsic state. This is the intrinsic state of the object that can be shared with others. When you call the operation, the class combines the internal intrinsic state with the explicitly provided extrinsic state. These two combine into the full state of the object, and the method can use this state to perform useful work. When this pattern is running, you will have one concrete flyweight instance for each unique intrinsic state. The other subclass of the flyweight base class is on the left, and it's called unshared concrete flyweight. This is a special case, and your implementation might not need this object, because this flyweight will never be shared with anyone. You might have some kind of edge case scenario in your application architecture, where you always want to create new instances of a flyweight, regardless of the intrinsic state. The unshared concrete flyweight class is intended for this very purpose. And finally, there's a flyweight factory. The factory has a factory method called getFlyweight, which expects a key parameter. This key uniquely identifies each intrinsic state. The factory uses a dictionary to return the concrete flyweight instance associated with the specified intrinsic state. You can add code to the factory that recognizes edge cases and always returns a new, unshared concrete flyweight instance for these cases. But again, this is optional. The client instantiates a flyweight factory, and every time it needs a new object, it calls the getFlyweight method. The factory uses its internal logic to either return a shared flyweight or an unshared flyweight. But the client doesn't care. It simply uses the object, calls the operation and provides the extrinsic state. I am going to use the Flyweight pattern to implement image loading code for a web browser. A typical web page contains a lot of images, but sometimes the same image appears in multiple places. It would be wasteful to reload the same image every time. So I am going to use Flyweight objects to load each image only once. So the first thing I need to do is examine the state of the image. What state information do I have? And is this intrinsic or extrinsic state? The image file name is intrinsic. The image position is extrinsic. And the image size is also extrinsic. The client is going to specify all of the extrinsic state, so I only need to store the intrinsic state. I am going to need an image class that derives from Flyweight and contains a file name member and a display method. I will not use unshared Flyweights in this example, so I don't have to implement the unshared concrete Flyweight class. So that leaves me with the following classes. Let's take a look at the code. I will start with the base image class, which acts as the Flyweight base class in this pattern. You can see that it sets up an abstract method called display, and that the display method expects arguments for the position and size of the image. This is the extrinsic state of the image, and it will always be provided by the client. Next up is this concrete Flyweight class called image. The image class derives from base image and has a protected string field called image file name. And this is the intrinsic state of the image, and it is stored inside the object. You can see that there's a constructor here for initializing the image with the file name. Okay, so now the display method has access to the full state. The intrinsic state is stored in the field, and the extrinsic state is provided in the method arguments. So now all the method has to do is combine this data and do something useful with it. You can see from this code here that the method simply generates an HTML image tag with all the information and writes it to the console. If this were a real web browser, you could have the image class actually load the image into a bitmap and render it on the screen every time the client calls the display method. Next up is the image factory. It uses the factory method pattern to set up a factory for generating image instances. I use the image file name as a key. I look the image up in a dictionary and I return it. If the image doesn't exist, then I explicitly instantiate it, add it to the dictionary, and then return it. You can see that I added some extra console write-line commands, so we can check that the factory is actually working correctly. And finally, here is the web page renderer class, which acts as the client. It instantiates an image factory and then uses it to instantiate the same image 3 times, but each time with a different position and size. I'll conclude with the main program class. The main program method simply instantiates a web page renderer and asks it to render itself. That should output all 3 image tags. Let me run the program to prove that everything is working. I'm compiling the code now. And now I'm running the program. Here we go. And there you go. The program created one single image instance, and then it reused that instance twice for the other two images. But despite that, each display method call combined the intrinsic and extrinsic state to produce the correct output. Everything works. Okay, here is a quick checklist you can use to implement the flyweight pattern. First, make sure you need to support a very large number of fine-grained objects efficiently, and that the extrinsic state information of each object can be retrieved quickly and on demand. Then split the object state into shareable intrinsic state and non-shareable extrinsic state. Remove the extrinsic state from the object and add it to the calling argument list of all affected methods. Create a factory that can cache and reuse existing class instances. Change the client to use the factory to request objects. And finally, change the client to look up all extrinsic states and provide that information to all affected methods. And here are some final comments. The key thing to remember with the flyweight pattern is that it requires you to look up the extrinsic state on demand. So you need to have this data available in some kind of fast medium. If it's an external database, that's perfectly fine, but make sure the database has fast read access. The reason for this is that you need the extrinsic state every time you use a flyweight object. If there is a performance hit when accessing extrinsic state, then you will experience this hit every time you call any method on the flyweight object. So make sure you have fast access to this data. You often see the flyweight pattern combined with the composite pattern, because it's an excellent way to minimize the number of leaf object instances in memory. If the leaf nodes of a composite data structure have a simple state that you can quickly look up on demand, then you will get a big improvement in memory footprint by combining these two patterns. Okay, let me conclude by summarizing what we have learned in this lecture. The flyweight pattern allows you to support a very large number of fine-grained objects efficiently. A requirement for the pattern is that the state information of each object can be retrieved quickly on demand. The pattern reduces the number of flyweight object instances in memory by sharing them among clients. To use the pattern, you need to split object states into a shareable intrinsic state and a non-shareable extrinsic state. The flyweight pattern is often combined with the composite pattern to reduce the number of leaf object instances in memory.